We go over rotation equilibrium and ladders. First question. A 10 meters long ladder of mass 8 kg leaning on a wall 8 meters from the ground is shown. Find all the forces acting on the ladder. Now the first force that we need to be familiar with is the weight force, which acts on the very middle of the ladder. That is going to be the weight force mg. Now we have got the height of the to where the ladder is as 8 and the length of the ladder as 10. Now what will be this distance here? So we can use triangles. I'll get this as a small triangle there, where this, of course we know if this is acting on the middle, then the distance from here to there is 5. So this is going to be 5. Let's name this as x. And then we have got a bigger triangle there, where this is 8 and the hypotenuse is 10. Now what will be x? So 5 divided by 10. So this side, which is corresponding to this side, should be equal to x divided by 8. If we cross multiply here, that will give us 10x is equal to 5 multiplied by 8. We divide by 10. X is going to give us, of course, 5 can go here, 5 can go there. It will be a 2. 2 into 8, that is going to be a 4. So this is 4 here. And if that is a 4, we know that the hypotenuse of this comma small triangle up to just this point is 5. What will be this distance? Using the Pythagoras theorem, that is going to be, let's name it y. If this is y, then it is going to be 5 squared minus 4 squared. 5 squared is a 25, 4 squared is a 16. 25 minus 16, that is a 9, and the square root of 9 is a 3. So this distance is 3 here. Now let's go on and work out this one. So the first forces we need to consider the forces in the y. Well, I just broke the weight force, that is one force that is acting on this object, but there's also a component of the force balancing the ladder at this point. That would be, let's call it the component in the y. There's also a component in this direction, that will be the component in the x. There's also a force which is making 90 degrees here, balancing the ladder with the surface. Let's call it the normal force, because it is making 90 to the surface there. Okay, so the net force in the y, we can see Fy is going up and mg is coming down. Because it's not moving, the net force is going to be equal to 0. Fy minus mg, the mass is 8, g is 9.8. So this will give us Fy being equal to 8 multiplied by 9.8, that is going to be 78.4 newtons. Considering the net forces in the x, this is going to be equal to the only force going in the positive x, that is Fx, minus what is going in the opposite direction is the normal force there. And also here it is going to be 0 is equal to Fx minus normal force, because there's no movement. This will give us therefore Fx being equal to the normal force, like that. Okay, now we are done with the forces. Now let's consider torques, because this thing is able to rotate. Now the net torque acting on this object, we are going to take this point, the very down, as a fixed point. So first we are going to consider at the very end, what are the torques going in this direction. So we can see there is a normal force there which will be causing motion in that direction. But this normal force is making 90 degrees with the 8. So if we multiply the normal force by the 8, that is going to give us a torque. Of course, we could have also used the component of the normal force, which makes 90 degrees with the ladder here. But if we did that, then we would have used the distance as 10, and then the component of the normal force here. Of course, this angle theta is going to be the same as this angle theta here. So this will be normal force sin theta. So we would multiply this by 10. So if there's an easier way to do it, let's follow that one. And then from here we are going to, this is the only force that is going to cause motion in this direction. Now what of motion in the opposite direction? we can see that the only force which can cause rotation in the opposite direction is the what? Is the weight force, mg. And mg we can see, okay, this is a force which is making 90 degrees at this point with the 3 there. So we're going to say minus 3 mg. Again, we could have also used the component of mg, which is making 90 degrees to the ladder like that. And this angle here is theta. And the side is adjacent, this side which I've drawn is adjacent to theta. So we could have said mg cos theta. And then the distance which is perpendicular to mg cos theta, that would have been 5. So we would have used 5. That could be the same. Okay, so the net torque is going to give us 0, and that will be equal to 8n minus 3. The mass here, of course, mg gave us 78.4. So if I multiply 78.4 by 4 by 3 first, 78.4 multiplied by 3, I'm going to take 8n the other side. That is going to be negative 8n is equal to negative 235.2, and then divide by negative 8 both sides. We're going to find that the normal force there is going to be 29.4 newtons. So that is going to be it. Now we know that Fx is equal to the normal force. Therefore, even Fx here is going to be 29.4. So these are the forces which are acting on this object. Now if we put this component and this component, they are going to give us a resultant which is F, which is equal to the square root of Fy squared plus Fx squared. So that is going to be 29.4 squared. If we calculated Fy, that is 78.4 squared, and then square root that. So that is going to give us 83.7 newtons. That will be the net force which is acting there. Alright, this is all for the first question. Let's proceed and look at this one. Given a ladder of mass m leaning on a frictionless wall and held by a coefficient of static friction of 0.7 to the ground, find the minimum angle the ladder makes with the horizontal before it can slip. So I want the minimum angle here, theta, that the ladder can make before it can slip. Now, what are the forces which are acting on this ladder? Of course, the first force we should understand is the weight force, mg. Now, we have been given that there is a coefficient of static friction to the ground. So there is actually static friction which is balancing the ladder in this direction, because it can slip if it goes in that way. And also we have got a component that is a normal force at this point. Let me call it normal force 1, because there will be also another normal force making 90 degrees to the wall there, normal force 2. So these are going to be the forces which are acting on this ladder. Now let's start first with the forces in the y. Considering the forces in the y, sorry for that. Okay, the forces in the y, the net force in the y is going to be equal to the force which is going up. We have got n1 minus what is going down. We have got mg, and the net force is going to be 0. So that will be n1 minus mg. We don't have mass, so just put 9.8 there. So that will mean n1 is equal to 9.8 m. Now let's consider the forces in the x. Forces in the x, the net force in the x is going to be what is going in the positive direction of x, that is the static friction, and then minus mg, I mean n2, that is the one going in the opposite direction, that is n2. So if this is going to give us 0, and we have got static friction which you found by coefficient of static friction multiplied by the normal force, and then minus n2. So if I take n2 the other side, n2 is going to be equal to coefficient of static friction times normal force. But how do we get to find the normal force? Normal force is also given by mg. So N2 therefore is going to give us mu, which is 0.7, and then m we don't know, we know g, which is 9.8. N2, that is going to be equal to multiplying 0.7 by 9.8. That will give us 6.86 m. Alright, so this will be another equation, equation 2. Now we have got a lot of unknowns. We don't know N1, we don't know N2, we also don't know the mass. But how do we get to the answer? We can work now with torques. Okay, we can now work with torques. So we're going to get a component on this point which is making 90 degrees with the ladder. And that component, of course, if this is theta here, then even the angle at this point is going to be theta. And if we can draw a line which is parallel like that, this side is going to be equal in magnitude to this side because they are parallel lines. And we can see that this side is going to be opposite to the angle theta. So we're going to say N2 sin theta. So even this one is going to be N2 sin theta. Even the normal force, I mean the mass times gravity, we're going to make a component which makes 90 degrees to the surface. And even this angle here is theta. Now we can see that this side is adjacent to the angle theta. So it will be mg cos theta. So looking at the net torque is going to be equal to the torque in the anti-clockwise direction is N2 sin theta multiplied by the perpendicular distance. The perpendicular distance, that is the distance of the ladder. We've been told we don't know the length of the ladder, so let's just call it L. Okay, so that will be the length L. So we're going to multiply this by L, and then minus what will cause rotation in the opposite direction. We only have this, and that will be the component of mg, that is making 90 degrees to the surface. So that is mg cos theta. Now what is the length? The distance from there to there. So that is just half of L. So we'll say L over 2. Well, the net torque is 0. That is N2 sin theta L minus mg cos theta L over 2. Now we know that N2 is here, is 6.8 m. So we can substitute there. And I can take this term the other side. So that will be N2. Where there is N2, I'm going to put 6.86 m, and then sin theta L, and that will be equal to, this is going to remain positive because it goes the other side, mg cos theta L over 2. So the mass here is going to cancel out with the mass there. The length also cancels with the length there. So remember 6.86 sin theta is equal to, of course, g is 9.8. We have got a 2 there, so over 2, and then cos theta. 9.8 divided by 2, that gives us a 4.9. So this is 6.86 sin theta is equal to 4.9 cos theta. I can divide both sides by cos theta. This cos and the cos there goes, so we're going to remember 6.86 sin over cos, that will give us tan theta, and that is going to be equal to 4.9. So to remain with tan theta, I'm going to divide both sides by 6.86. So for 4.9 divided by 6.86, that is going to give us 0.7142. So to remain with theta, theta is going to be tan inverse of that value. So theta is giving us 35.5 degrees. So that is going to be the minimum angle that the ladder is going to make before it can slip. Let's proceed to this question. A uniform ladder of length L and mass 20 kg rests with its base on a rough horizontal floor and its top on a smooth surface. So the surface here is smooth. We know the length here is L. Find the coefficient of static friction just before the ladder can slide. So let's first look at the forces which are acting on this ladder. The first force, of course, is mg, acting on the very middle. And the other force, we want to find the coefficient of static friction just before the ladder can slip. So here we are going to have a static friction that is going to be balancing the ladder so that it does not slip. And then we are going to have a normal force 1 here. We also have a normal force here, another one, N2. Now let's look at the net forces acting in the y direction. Net forces in the y, we have got N1 going up, and then mg is going to be negative going down. Net force supposed to be equal to 0, that will be N1 minus m. The mass is 20, g is 9.8. So N1 is going to give us 196 newtons. Now looking at the net forces in the x, we have got the static friction, and then minus we have got N2. So the net force, of course, is going to be 0, and that will be static friction minus N2. Taking N2 the other side, N2 is going to be equal to static friction. Now, the static friction, we know it is given by mu s times the normal force, which is given by mass times gravity. So N2 is going to be equal to mu s. That one we don't know, that is what we want to find. The mass is 20, gravity, that is 9.8. So this will give us N2 being equal to mu s times 196, which we can also say mu s is N2 divided by 196. Alright, now let's look at the torques acting on this object. If we make a force making 90 degrees to this surface, of course this is theta, this is going to be N2 sin theta. We can make a force making 90 degrees also to the ladder. This is going to be mg cos theta, because this is theta here. So the net torque acting is equal to, first what is going in there anti-clockwise, we have got N2 sin theta multiplied by the length of the ladder, which is L. And then what is going in the other direction, we have got mg cos theta. The length is L over 2 because mg acts on the middle. So the net torque is 0, and that will be N2 sin theta L. Of course, I can substitute the value for theta, which is 60, and then multiplied by L, minus the mass is 20, g, that is 9.8, and then cos theta, which is cos 60, and then the length, that is L over 2. I can take this term, the other side becomes positive, so that will be N2 sin 60 L is equal to, this is going to become positive, 20 times 9.8, that is 196, and then cos 60, we have got L over 2. The L can cancel out with the L there, and I can just work out what sin 60 is. So sin of 60 degrees, that is 0.866, and then N2, that should be equal to cos 60 is a half. So this is a half multiplied by another half there, that will be 1 over 4, and then multiplied by 196, that is a 49. So to remain with N2, we are going to divide 49 by 0.866, and that is going to give us 56.58 newtons. So to remain with mu s, will come in this equation, and where there is n2, are going to put 56.58, so divided by 196. So the value for the mu s, which is the coefficient of static friction, is going to be 0.2887. Alright, now let's consider a last practice question here. A 70 kg man stands on a 10 kg ladder as shown. Calculate the coefficient of static friction when the ladder starts to fall. Now firstly, what are the forces acting on the ladder? Here we have the ladder like that. Of course, the ladder itself has got a weight force. So the weight force of the ladder that acts on the very middle of the ladder, mg, and I'm going to call it capital M and then G, that is to represent the ladder. And then we also have a man on the ladder, so there's also another weight there, which is, I'll call it small mg. And then on the ladder we have got this force making 90 degrees, making 90 degrees with the surface, that is going to be, let's call it N2. Of course, we have got also another normal force here, N1. Now, because we're talking about static friction, then there's also static friction in this direction supporting the ladder. Static friction. Now I want to calculate the coefficient of static friction. Alright. So let's first consider the net forces in the y. The net forces in the y, the upward force supporting, first the upward force supporting the ladder is N1. The downward forces, we have got M1, mg, and then capital Mg, because we have got two downward forces from the man and also from the ladder. Of course, the net force is supposed to be equal to 0, N1 minus the mass of the man is 70 multiplied by 9.8. Mass of the ladder is 10 multiplied by 9.8. And so if I take, first I'll say 0 is equal to N1 minus, let's multiply 70 by 9.8, and then add 98, which is 10 times 9.8. So that is 784. I'm going to take it the other side, so that will be N1 is equal to 784 newtons. Now considering the net forces in the x, that is going to give us, what is going in the positive x is static friction, in the negative x, that is N2. So this of course is going to be 0, and then we've got static friction minus N2. I'll take N2 the other side. N2 is going to be equal to static friction, which is mu s times mg. Okay, now mu s therefore is going to be equal to N2 divided by mg. Mg, this is the mass of the ruler, the ladder itself. So I've got N2 over mg for the ladder. We've seen the mass of the ladder is 10, so that is 98. Okay, like that. Now we can proceed from here, and let's look at the net torque acting on this object, which is our ruler. So the net torque, first, what is going in the anti-clockwise direction, we only have N2. But because we have the distance which is making 90 degrees with N2, we can use this very distance instead of finding the component there. So that will just be 9 multiplied by N2. Now those going in the other direction, we have got minus. We have got the weight of the person here. We can see it's making 90 degrees to the surface, and the distance here is what? 8. So the weight of the person and the distance 8 are making 90 degrees, so we can just use 8. We'll say 8 times the weight, which is mg. We also have another one here. We also have the weight of the ladder itself. like that. Now we know that the ladder is 15 meters long. So for the ladder, what I can do is, if I break this into components, we are going to have a component which is making 90 degrees like that. We are going to have the angle theta here. But of course, we don't even know the angle theta. So what I can do is, I'll use just triangles to find the value of this height. So I've got a small triangle where the distance from the very middle, from the very beginning to where the mass of the ladder is, that is half of 15, which is 7.5. And then we don't know this height h. And then we have got now the very big one, the ladder itself, with the whole distance of the ladder, that is 15. So we have got 15, and also the height here is 9. So what would be this distance here? So to find that distance, 7.5 over 15 should be equal to x over 9. So if we cross multiply to give us 15x is equal to 7.5 times 9, dividing both sides by 15, x is going to give us 9 divided by 15, that is 9 divided by 15. Okay, so of course the 15 here and the 15 there cancels. 7.5, just a moment, I divide this. Okay, 7.5 into 7.5 is a 1. 7.5 into 15 is a 2. So 2 into 9, that is 4.5. Like that. So if this side is 4.5, what will be this distance here? That is what we want. So we are going to use the Pythagoras theorem. 7.5 squared minus 4.5 squared, and then square root that. So this distance here is 6. So you can see that it's making 90 degrees like that. So we're going to use 6 here. So you can just say 6 times the mg. So the net torque is going to be equal to 0, and that is 9 n2 minus 8. The mass of the person is 70 kg, and 70 times 9.8, that is going to give us 70 multiplied by 9.8, 686, then minus 6 mg, that is 10 times 9.8, that is going to be 98. So this will be 0 is equal to 9 n2 minus, so if we calculate this value here, 686 multiplied by 8, that is 5,488. If we multiply 6 by 9.8, 98 I mean, that is going to be 588. So let's sum up these two values. That is 0 is equal to 9 and 2. 588 plus 5488. So this is going to be 6076. I'm going to take this value there, so that will be 9 n2 is equal to positive 6076. So to remain with n2, that is going to be equal to that value divided by 9. This is going to be 675.11. Now we can find our coefficient of static friction. Mu s is going to be equal to n2, which we have found as 675.11, divided by 98. So divided by 98. So actually the value for the normal force second is just fine, but just the value in the denominator here on this second expression is what is not fine. So it's supposed to be 784 in the very denominator there. So let's look at that. How did we get to find it? That is in the net forces in the x direction. Let me just repeat that. So the net forces in the x, we were saying what is going in the x, we have got static friction here, and then we have got also N2, like that. So the net force is 0 there, and the static friction, we know it is the coefficient of static friction multiplied by the normal force, and then minus N2. Okay, that is what it gave us. Now at this point we are going to take N to the other side, so that will be coefficient of static friction times the normal force is equal to N2. But what of this normal force we're talking about? So if we want to remain with mu, that is going to be N2 divided by the normal force. Now this normal force I used here, I just got to use the normal force. I don't know even the normal force, I just used mg. But the normal force we are using, this is the normal force at this point. Okay, that's the normal force we are using. Why are we using this value which is here? If we look at this, we are saying the static friction at this point, because we have got static friction in this direction, we also have N1 in this direction. And we know that static friction is equal to coefficient of static friction multiplied by the normal force. So the normal force is here. That is what we are using. Unless if we didn't have any mass here, the normal force here would have just been equal to mg. But because we have another mass, so the normal force is going to be a combination of the mass of the ruler multiplied by gravity and also the mass of the person. Okay, so the value is there. So that is where now we are punching. Mu s is going to be N2 over the normal force we already calculated, that is 784. So 675.11 divided by 784, that is mu s is going to be equal to 0.861. So that is going to be the answer then for this question. Well, thank you so much for watching the video. Stay blessed.